Hello to those watching this recording in the future. I'm David. I'm the coordinator of the Maths Learning Centre here at the University of Adelaide. It's semester 1, 2024, and this is a revision seminar for Statistical Practice I. And that's enough of my great big face on the video. We will go to the camera. So, the first thing we're going to talk about is ANOVA, which is short for Analysis of Variance. And the word variance was created specially for ANOVA. Up until then, we only had standard deviation as a terminology, but then Fisher created the word variance to describe a part of the calculation that's involved in ANOVA. And some people will pronounce it ANOVA, but I pronounce it ANOVA. Yeah. And the first thing to know about any statistical procedure is the kinds of questions and data it goes with. Statistical procedures are designed to answer questions using data, and you need to know the kinds of questions it can answer. An analysis of variance answers a yes or no question. Like all hypothesis tests answer a yes or no question. And I know it answers a yes or no question because it produces a p-value. And it answers the yes or no question, which is this. So this is the kind of yes or no question in science that ANOVA answers, and it is this is not how your lecturer will have said it, but this is what's in my head. Does being in a different category make a difference to the number outcome? That is the kind of question that ANOVA answers. The idea being that you may have several different categories, such as, the type of treatment someone gets in a medical experiment, or the kind of food you give your animal, or the country they were born in, or any number of things, and some numerical measurement that you've made on all of your individuals, and you want to know whether one of those things affects the other. So this is a picture in my head of how it works. There is some numerical outcome. And I draw this like this because that's a scale on which to measure my number. And I want to know, does being in a different category, these are the boxes to put people in, or cat or chickens or whatever they are, does this make a difference to this? Does this make a difference to that? That is what ANOVA is for. And it is especially important that ANOVA is designed when different individuals are in different groups. These are all different people in these groups. I mean, there's probably like 10 in each group, something like that. But what you don't have is people in different situations being measured multiple times. So that is the picture in my head that goes with this. If you ever watch any of my other videos on statistics, these will feature. And if you ever ask me at the Maths Learning Centre about how to choosing what stats goes with what, I will draw pictures like this. So, yeah. Right. That is what the sort of the science question that goes with it. Your data will have a list for each person, or pig or cat or petri dish or school or whatever they are. It will have your subject, which is the person or object that's under study, and it'll be like this. And then it'll have like what category they're in and what the number is. And it'll look like this. So like A, and there'll be numbers here, and then B, and there'll be numbers here like this. And the data will tend to look like that. Tend to look like that. They may, or the categories may all be mixed into each other. That's possible. The computer doesn't care. It can tell what to do in R. But if your data's set up like this, then you can do ANOVA. So at this point, does anyone have any thoughts or questions? If it was a two-way ANOVA, it's a great question. That is one-way ANOVA because there's one way to affect the outcome. But with a two-way ANOVA, has two ways to affect the outcome. So you'll have some categories here and some categories here, and a number as the outcome. That's what two-way ANOVA is. There are two ways to affect the outcome. And each of these variables will have a column in the data. So the data will tend to be, oh gosh, I've run out of letters. Let's call this A, B, and C, and let's call this, yeah, 1, 2, 3 is fine. And so the data would look like this. I'll call this category 1 and this category 2. And so it would have your people, or whatever they are. It might not have this column, but R will have it on the side anyway. I have numbers. There'll be like category number 1, and these ones might be in number 1, and then like that. And then it'll have category number 2. And so maybe there'll be A, B, C. Something like that. So that the ones go with different A's and B's, and then everything will have a number of its own number outcome. That's how it should look in R in order for it to do its job. You may have it, this wouldn't happen in the exam, but in real life, if you collected this data, you might do all of the 1s on one day and all of the 2s on another day and all of the 3s on another day. And they'll often end up being in different Excel sheets. In order to get R to do what you want, you have to put them all together into one big thing. Does that answer the question? And it's really useful when you're thinking about any statistics procedure to know what kind of question it answers, that's so far, and what the data should look like in order to do it. Now, for the purposes of your exam, how the data should be arranged is probably not important, but they may show you what the data is arranged like, and that may give you a bit of a hint on what statistics is supposed to go with it. Okay. So one-way ANOVA and two-way ANOVA are designed to answer similar questions of does being in a different category make a difference to the number? But two-way ANOVA asks there are two different kinds of categories to be in. And it does the word interaction mean anything to you for two-way ANOVA? Interaction? No? Okay. That's a thing you can do in two-way ANOVA, so I just wanted to check. Okay. So I'm going to go back to one-way ANOVA. Oh, so if someone says ANOVA but doesn't tell you that it's one-way ANOVA, they mean one-way ANOVA. If it was two-way, they would have said. So if someone just says ANOVA, they mean one-way ANOVA. So back to one-way ANOVA. It's designed to answer questions like this. Doesn't matter how many categories there are, but usually it's 3 or more. If there were 2 categories, you would do a t-test. Or a Mann-Whitney U-test, but you know. If there were 2 categories, you do a t-test. But you can do ANOVA with 2 categories if you want. It's just people will look at you weird and say, why didn't you do a t-test? So there's usually 3 or more categories. But back to one-way ANOVA, statistics is not very good at answering questions like this. It tends to answer questions about parameters, about unknown numbers that describe a population. And so if you want to do a hypothesis test on a question that concerns data, you actually have to ask the question about the proper numbers that are involved. So the question you're going to ask is, all the people who could be in this category will have a mean for what this number is. And all the people who could be in this category have a mean for what this number is. And same for this one, and same for this one. I'll answer that question in a second. And same for this one. And your question is, if being in a different category didn't make a difference to the number outcome, then that would mean that all those means should be the same. Because if it did make a difference, the means would be different. So I've just had a question. You only have one past exam paper. Is there any way to get more practice? Yeah, I don't have access to anything other than, well, I don't even have access to your past exam paper. If you want more practice at things, there is usually a listed textbook or reference book in the course. It's probably called Introduction to the Practice of Statistics. If you have any textbook that says Introductory Statistics, it will have exercises in it that you can use. But just be careful because they will have slightly different terminology. But that's the only place I can look. And the other thing some people do is they go back to all of their pracs and tutorials and do them again as if they were exam questions. And I know that sounds like a weird thing to do, but some of those do they call them tutorials or workshops? Tutorials? Some of those tutorials are weeks and weeks and months ago, so you will have forgotten the answers by now. So you can go back and do them again. I'm sorry, that's not very good advice. That's not very satisfying, but that's the answer I have. Yeah, but any textbook that says Introductory Statistics in the title should do the trick. But there's probably one listed in your My Uni course that says this is a suggested textbook. Have a look and see what you can find. It used to be called Introduction to the Practice of Statistics, but it might be called something else now. So where was I? One way ANOVA. Right, okay. So it is a yes or no question that it answers, and yes or no questions are answered by hypothesis tests and p-values, that sort of thing. So yes or no question means hypothesis tests. And a hypothesis test means p-value. So the only way to do a hypothesis test is to have a hypothesis to test. And so you need a null hypothesis. And your null hypothesis, that's how they write it, yeah, with an H0. And your null hypothesis is that the mean in one group and the mean in another group and the mean in another group, and however many groups there are all equal to each other. And the reason we've chose that as our null hypothesis is that if being in a different category did not make any difference to the number, all the means should be equal. And statisticians like means. They're useful things. And the other reason we've chosen as our null hypothesis is that yes or no question. We have to pick one of the answers to be the null hypothesis. And we've chosen the answer, no, it doesn't make a difference, because there's only one way for all these means to be the same, but there are very many ways for the means to be different. And to do the calculations that we need to do this, to do a hypothesis test, you have to pick things being equal. Otherwise, you have no way of figuring out the calculations. So the null hypothesis is that these are all the same, and then you have to tell the reader what those stand for. So there's a bit where your lecturer will usually say, define any parameters you use. A parameter is these letters here. They are parameters. And so you would say where mu1 is the mean of all individuals in category 1. And so on. Mu2 is the mean of all individuals in category 2, and so on. You would put them all down. But normally it wouldn't be called category 1. It would be called the mean of all individuals who had oats, and the mean of all the individuals who had wheat or whatever. Like, you would have to actually put it in context. But anytime you mention a letter, you have, unless it's like a T or Z, you have to tell the reader what it stands for. Yeah. So that's your null hypothesis. And then your alternative hypothesis, H, they use a capital A or a small a or a 1? Small a. They are the options in the various other stats courses from other disciplines. The alternative hypothesis is that not all the means are the same. And the easiest way to write it is in those words. It's not the same as just putting a not equal to sign here, because it's like, if they're all the same, it's still not all the same if just these two are different and those two are the same. So you just have to say not all the means are equal. That is, because there are many, many ways for them to not be all the same. So, yeah. Okay. Cool. And that is the beginning. We haven't actually done anything yet. We've just got some parameters. And usually at this point, if you did a t-test, you'd have like an X bar and a mean standard deviation, blah, blah, blah. But ANOVA is not designed that way. ANOVA is extremely clever. Fisher, who invented it, was a very clever man, and also quite arrogant, and refused to explain anything that he thought was obvious, which is why it's so confusing these days, right? 100 years later, it was invented about 1925. 100 years later, we're still all a little confused. But I'm sure that our good professional statisticians have understood all the details. But you can get a bit further without having to do all that theory. This is the picture that's in my head when I think about ANOVA. These are the categories you can be in, however many there are. And this is the numerical outcome here. And then each person in part A, you can draw where their outcome is, for example. And so there's all these people here, or rabbits, or whatever they are. And it might look something like that. And you can see, without even doing any calculations, that the ones in D have lower values than the ones in A. Almost all of these people are lower than almost all of these people. And you can see that C is higher than B, but it's not that much higher than A is. They overlap a lot here. And what ANOVA is trying to do is figure out how much overlap is there, and try and compare it to what could have happened. So if all the means for all possible people who could be in these categories were in fact all the same, you would have expected these all to look similar to each other. You would have expected them all to be near the middle of whatever this is. And also, if they are all the same, then this isn't really 4 different categories, because it doesn't matter which category you're in. It's just one great big one group. If all the true means it should be something more like this. Right, that's what we would have expected to happen. That's what it should be. Maybe we just by random chance happen to pick a group of A's that are up here. And maybe by random chance, we happen to choose a group of B that are down here and a group of C's that are here and a group of D's that are down here. Maybe just randomly, those are the people we happen to pick for our study today. We would like to know, how unlikely is that? That's the question we're going to answer with our p-value. How do you feel about that as an idea? I mean, that's what all of your hypothesis tests are about, trying to imagine what could have happened if everything was the same, and then say, how likely is it for them to be as different as they are in my sample? That's what we're going to figure out. Now, it seems pretty unlikely to me to just happen to pick all your A people randomly to be the ones at the top. But that's what all the calculations are for. You don't just do it from the graph. But if I did see this graph, I would go, yes, this ANOVA is going to come out as significant with a low p-value just because of the way it is. Okay, so radio. It should be this. And so we're going to compare this to that. That's what we're going to do. And the way we're going to do it is this. I'm going to redraw my picture again, but bigger. What we're going to do is we're going to figure out the mean of all of them as if it was one giant group. We put them all into one big group and find the overall mean of the whole thing all together. And that will be maybe about here-ish. I shall call this the grand mean. And we're going to see how much variation is there if we just assume it's one giant group. And that will be this, just the standard deviation, like the variance. And so we're going to figure out how far everything is from this grand mean. And so we're going to find all of these distances here. And these distances here. And these distances here. And then we're going to square them and add them all up. And that is the sum of squares total. SST, does that sound like a thing? I'd have to look this up in your course, actually. And then what we're going to do, well, actually, we're not going to do this. The computer's going to do it for us. But then what we're going to do is the same thing again. But now we're going to say, if I wish I'd known that I was going to do ANOVA before I started this, so that I had all these pictures pre-prepared. That would have been great. Then what we're going to do is we're going to say, well, what if they really were 4 different groups? And then the amount of variation is just how far it is from the local group mean. So we're going to figure out a group mean for every group. So this is the mean that goes with group A, and this is the mean, not the actual X bar A. This is the mean that goes with group B, and this is the mean that goes with group C. They probably do it with a Y, don't they? Anyway. And I'm going to figure out how far everything is from those means. And square them and add them up. Lastly, I'm going to figure out how far all of these means are from the grand mean. It's getting worse, my drawings. I'm going to figure out how far each of these is from the grand mean. And I'm going to compare all of those differences. If all of these group means are all close together, then it probably means that the 4 groups aren't all that different. But I want to compare that to how spread out everything is within the groups. And actually, even more, I'm not going to just have this one. I'm going to have this difference once for every person who's in this group. Okay, So I'm just going to draw one more pair of pictures. If the means really were here, if your data was really tightly packed like this, then you would conclude definitely that being in a different category makes a difference to the number. But if they were spread out like this, then you couldn't tell. Because a person in this group could be way lower or higher than a person in this group, whereas all the people in this group are higher than all the people in this group. And so it matters how spread out each group is in order to make your conclusion. This you say, yep, definitely. The group matters. But this one, not sure the group matters. So even though all the group means were the same distances from each other, because there's a lot more variation within the groups, this one I'm not so sure, but this one I am sure. So both of those things make a difference to the result. If the groups of means are far apart from each other, that'll make you more sure, but if the spread is wider, that will make you less sure. Okay, cool. Does anyone have the ANOVA bit of my uni or their notes handy that I could have a look at? So much. And look, I've actually done almost the same thing that your lecturer did, but they had a fancier R graph than I had. But mine's more fun. Okay. So bear with me. Oh, they even just did it in words and didn't do formulas. Did they do formulas later? Yeah. I've got spread of the group means around the grant mean divided by spread of observations around the group mean. Okay. So I'm going to show you something. Okay. Thank you. I will give this back in a minute. So when you ask R to do an ANOVA, so just let me do an example. When you ask R to do an ANOVA, you will, why do you not show this to me in the actual lectures? You horrible people. I'm pretty sure it's AOV. Does that sound like a thing? That would be in the Pracs, not in the lectures. The R code that you would write to get it to do an ANOVA. I'm just going to take a photo of this page. Oh, cool. You just reply to the email that this seminar told you about that one. There you go. You might come back to that, but I'm pretty sure it's AOV. to do an analysis of variance. Could be an LM, I'm not sure. Ah, what's that from? Thank you so much. I mean, LM is for regression, but also is for ANOVA. Anyway, we'll come back to that if we can find it, but if not, that's okay. So in R, maybe I'll come back to that. But I do know what the R will produce when you ask it to do that. It'll produce something like this. It produces response, and it will say the name of the variable here. So that would be our numerical variable. Thank you. Name of variable there. And then it will have this little table with all these headings, as long as you make it wide enough, otherwise we'll go on to the next row. And it will say the name of the categorical variable in this spot, and it will say residuals. And then it will say df, sum square, mean square, f value, and probability of being greater than f. It'll have a table that looks like that. And it will have numbers in all of these positions. It'll have a number here, and 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 a number here. That's what it will look like. It will spit out this sort of thing. And all of this information is enough to tell a statistician and the computer how to make the decision about the hypothesis test. The most important thing for the final decision of whether your hypothesis, what your hypothesis test answer is the p-value just here. That there is the p-value. And that there is the test statistic. All hypothesis tests have a test statistic and a p-value, and that's where they are in this table. All right. Yeah, damn it. Oh. And the way this table works is that this is excuse me. This is the sum of the squared differences between the means and the grand mean. That's this one. Once for every individual in the study. This is the sum of the differences between each individual and their local mean. That's this one. This is one less than the number of categories. And this is whatever you need to add to that to make it up to one less than the number of individuals. So the total here. And then this divided by that is this, and this divided by that is this, and this divided by that is this. It's cool, like it's weird. And that's really hard to describe on paper, but that's how it's done. So in the past, I don't know if your lecturer will do it. In the past, lecturers for this course have in the exam done something where they didn't fill out any of these three numbers and asked you to calculate it from what was there. Because if I do this divided by that, it produces this answer here. And this divided by that, it produces this answer here. And this divided by that produces this answer here. And you can see how clever Fisher was being. Like, honestly, who would have thought of that? It's amazing. And he invented all this for agriculture purposes. So it's really cool. He was, well, I mean, not that cool. He was trying to make wheat yield better. And he had all these variables involved. One of which was whether the local school had been given detention to remove the weeds from the wheat field or not. That was his last variable that he couldn't figure out why some years there were better yield, and it was because the local school was using the wheat field weeding as a detention. So anyway, that's all this thing. So in the notes, it says that the F statistic, the test statistic is called F for Fisher, who invented this. And it is the sum of the square, like they said, the total amount of variation around within the groups around the local mean. And this is the total amount of variation between the group means and the big mean. No, other way around. Now I really should have kept it on in front of me, but that's okay. But just so you know, it is the sum of the squares that goes with the category. Like it's in this spot in the table, sum of squares, name of category divided by the degrees of freedom that goes with the category. So you've got the sum of squares residual. Damn it. Damn me. Sorry. The mean square model, which is the thing that goes with this name of category here, which is in this spot just here, mean square that goes with the model, divided by the mean square of the residual. Those two things is what the F statistic is. And this thing is calculated by doing the sum squared of the model divided by its degrees of freedom. And this is the sum square of the residual divided by its degrees of freedom. I don't know if they teach you that in this course, but it's true. And so that's why there's all these divisions in the table that produce the final answer. And it's useful to know that the DF for the model is the number of categories minus 1. So if I had 4 groups, 4 categories, the degrees of freedom would be 3 for this spot just here. And it'll tell you the name of the categorical variable here. And so that degrees of freedom is 1 less than that. And then the degrees of freedom for the residuals is the number of individuals minus the number of categories. Yeah. So, for example, measure height of plants after growing in clay, sand, and soil. How many plants? Let's say 15. 5 each in each of those. So this is a setup of an experiment that would actually happen and actually did happen at Wake campus. Measure the height of 15 plants after growing in clay, sand, and soil. That's a numerical outcome, the height. And this is a categorical variable, which kind of soil it is. And so then you would say that the number of categories is 3. And so therefore the degrees of freedom that goes with the categories is 2. And the number of individuals is 15. And so the degrees of freedom for the residual would be 15 minus 3, which is 12. And you can check it. These two numbers should add up to 1 less than the total number of individuals, which they do. They add up to 14. So that's right. Yeah. So that's degrees of freedom. You can figure them out from the story. So in fact, if someone told you what these two numbers were and told you the story, you could figure out what this one, this one, this one, this one, and this one are from that information. It's pretty cool. And really, it's showing you all of that just so that you can check it's done its calculations correctly, basically. So once you've got your F statistic, then you have to look it up in an F distribution. Or the computer does that for you, of course. Because the imagining that we're doing here is we are imagining if this is what the data, if this is what all individuals who could possibly be in these categories could possibly measure, and we imagine all of the sets of data we could possibly have gotten, and therefore imagine all of the F statistics we could possibly have gotten, imagine all of them, some of them are going to be more likely than the others, and then this is the distribution of the F. These are all the Fs that could have been. All the Fs that are possible, given the null hypothesis. And your F will be here. That'll be your F statistic. And this area here is the p-value. And the smaller that is, the stronger your evidence is against the null hypothesis. It's all a big proof by contradiction, but with probabilities. So you're saying that if that's really small, then the chances of getting data like mine, if it really did if things that if what's possible for all possible people really is this, what are the chances of getting this? And if that's a low p-value, you go, nah, I don't reckon this is possible, because this was unlikely. Yeah. So that conclusion is the same for every hypothesis test. Got a low p-value, you reject the null hypothesis and conclude that there is a relationship after all. And the name of this distribution is the F distribution, because we're not very creative. So this is the F distribution with 2 and 12 degrees of freedom. But you can just call it, that's what I say aloud, but you can just call it F like that. And this is the one that goes with this example, but you would change these numbers based on what was in the table. You can copy them from the table. And that's because you know how, well, the T distribution only has 1 degrees of freedom. The T distribution only has 1 number for its degrees of freedom. And each T distribution has its degrees of freedom, and there's a different T distribution for every degrees of freedom, and that's great. But the F distribution has degrees of freedoms in 2 different directions. And so you need an address of both the street and the number to tell you which F distribution you're using. And this is enough information to tell a computer how to calculate the probability. Yeah. I'm not sure if you were taught how to make the computer calculate those probabilities. But you can tell it to do an ANOVA, and it's doing all this in the background. But the reason that we tell people this is because it's important to them. All hypothesis tests must have a description of the null hypothesis, a description of the test statistic, a description of the distribution of the test statistic if the null hypothesis is true. Yes, must have all of those things. And so if someone asks, you have to tell them, all of them. Yeah, and you would normally say, does your lecturer write statements like this with a twiddle? No? No, that's sad. If they do, this symbol means is distributed according to. So this statement means F is distributed according to the F distribution with 2 and 12 degrees of freedom. And that's how it's done. I mean, yeah, and then you make a decision based on what the p-value gives you. So I could theoretically make up some data and attempt to do one. I'm going to copy down the one that I was given. Let's see if my R works. Always takes forever to load. Not as forever as other statistics computer programs. SPSS, which is the one that they use over in social sciences, takes forever. Yay. So there's our studio for you. I'm going to just make up some data if that's okay. I should really just do this one, wasn't it? What was I saying? It was height and soil. Play. I'm sure there's a better way of doing this, but whatever. Oh, I can do it. Just a second. Repeat. Oh, I don't do R. I do it like once every 6 months. Let's see if that works. Yay. Okay, cool. Okay. I'm just going to put whole numbers in because I can't be bothered trying to think of anything better. Sorry. One, two, three, four, five. 1, 2, 3, 4, 5. 1, 2, 3, 4. Let's see if that works. All right, so there's my data there. Took me a while, but there's my data. I've got clay, and then some numbers, sand, and then some numbers, soil, and then some numbers. Cool. That's what my data looks like. Nope, it did not like that. That's okay. Okay, and then presumably I can do an ANOVA. Let's see. Height versus soil, I shall call it, so that I can remember what it's called. So I should be able to do height, twiddle, soil type, and then say that the data comes from this experiment. Does that look familiar? And see how I said height, twiddle, soil type? That is why I draw my things as number, like this little thing here. That's the same order that R puts it. So that's why I draw it that way. Okay, and then it's created a thing. It hasn't shown me anything, but it has put it over here. And then I should be able to tell it to do a summary of that, right? Height versus soil. Oh, that's weird. That's not what I wanted at all. Maybe I should tell it to do an ANOVA on that. There it is. Yay. It has produced this bit here, the analysis of variance table that I was talking about. And so the degrees of freedom here is 2, because there were 3 soil types, and so 1 less than that. This is our number of individuals, which is 15 minus the 3, so it's 12. Sum of squares came out to this, and 136 divided by 2 is indeed 68-ish, so that's right. And 18.8 divided by 12 is about 1.5, that sounds right. And then this divided by this is 43.7. And then it has said that the p-value is 3.09 times 10 to the minus 6. That's what this bit here means. And so that's saying it's actually 0.000003095, which is very small. And so since that p-value is less than 0.05, I would conclude that at the 5% level, I reject the null hypothesis and conclude that not all the means are the same. And therefore conclude that that there is evidence to suggest that soil type affects height. Well, is related to height. I don't know if it really affects it because I don't really know how the experiment was done, but that soil type is related to height. But what it doesn't tell me is which group is different to which group and which one's higher than which one, in which case I'm going to need some means to do that. So there is a final bit here. I mean, there's some earlier bits we're supposed to do before we do the ANOVA. We're supposed to check if all the data is normally distributed. We're supposed to convince ourselves that all the individuals under study are independent of each other. And we're supposed to convince ourselves that the standard deviations are all close together. So all of those things are things we're going to have to do. I wouldn't do them unless, well, if I was doing real research, I would do them. But in an exam, I wouldn't do them unless someone asked me to. So that's how to interpret that. But I'm going to say that if I had made these numbers closer together, it would have worked out differently. I wonder if I can get a plot of this. Let me draw. There it is. That's what my data looks like. Some of those dots are on top of each other. I'm sorry. I should probably do this. Like, there we go. That's exactly like my drawing before. And you can see that everyone in the soil, all the plants in the soil group are much higher than the others. I'm only seeing, I know, my mouse was on top of it. So none of these overlap at all with any of the other groups. So no wonder the p-value was so low. Yeah. But if any of these groups overlapped a bit more, the p-value would have been higher. So if I had changed this What's this one? Clay, and that one's about. I don't like it. Something's weird. Right, that's better. It moved them vertically up and down before. If I move some of these up and some of these down, then the p-value would have gotten higher because the groups overlap a bit more. That's how it would have worked out. Okay, fine. Yay, ANOVA. But what we're supposed to do is follow that up with some pairwise comparisons. I think that's what your lecturer would have called them. I'm going to look at your screen again. You've still got it there. No, you sent it to me. Okay. Thank you for your grace with my scattiness here. Yes, please don't use stupid machine. Yep, of course you are. That's because I sign in as me instead of the Maths Learning Center. I give up. So I'm just going to look at the screen. Yes, please. So our big question that ANOVA answered was, does the category make a difference to the number outcome? I'm just going to close. Damn you. Our big question that ANOVA answered was, does being in a different category make a difference to the number? And we've come up with an answer with our plants of yes. But it hasn't been specific about exactly which category makes the biggest difference. And so now we have to ask a whole lot of new questions, which is being in clay different to being in soil? Is being in soil different from being in sand? Is being in sand different to being in clay? We have to ask all of those comparisons between just two of them. So you will get an answer for, are all the means the same? But you will not get an answer for is this mean different to this mean? And you will have to ask all of those questions separately. So we get that answer, but we need to ask, is this mean different to this mean separately? And those things are called multiple comparisons or pairwise tests. Wait. These things are called pairwise tests. And so if there's three of them, then there's three pairs. Are these two different? Are these two different? Are these two different? If there's four of them, then there's six pairs. These two, and 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 these two. And the more of them you have, the more of them there are, but faster. It goes up very quickly. It goes up in a quadratic sort of way. So there's all these complicated T statistics that are involved there, and there's all these degrees of freedom. But what you can do is ask the computer to do it for you. And we're going to use Tukey's HSD test. HSD stands for Honestly Significant Difference. He won an award for that, actually, did Tukey. Yep. And Tukey also invented the box plot, by the way. Okay. Did you do box plots? Yeah. Tukey invented the box plot in the 70s, 1970s. So it's actually all quite recent, this stuff. So, yeah. So Tukey's Honestly Significant Difference test. I should put that in. And you can ask R to do that for you. I'm almost certain that I am capable of making it do that. Let's give it a try. Let me just hope that it knows what to do. Tukey HSD. And what do you put into Tukey HSD, pray tell? A fitted model. Okay. Well, that was called height versus soil. Ah, you ridiculous person. So maybe I should have done AOV. And there it is. It's got the difference and the lower and upper confidence interval and a p-value. And that p-value has been adjusted, it says edge, so that it makes it harder to accidentally find differences that aren't really there. Because if I was doing like if I had 5 groups, there'd be 10 comparisons. If I had 6 groups, there'd be 15. And if there were 10 groups, I'd have like 45 of them. If something happens 5% of the time and you do it 50 times, it's probably going to happen like that 5% that you do with the p-values is the chances of getting accidentally saying that there's a difference when there isn't. And if you do something 50 times, and something happens, and being wrong happens 5% of the time, probably going to happen once, right? So there, they've done that. But look, they're all significant. They're all like 0.0. Significant's a bad word, probably. They're all under 0.05. And so I'll declare that sand versus clay, which is this one here, there is a significant difference there. Soil versus clay, it's significant. Soil versus sand is significant. And so, yep, we would say that they're all have low p-values, and so there is strong evidence to suggest that all the different soil types affect the outcome. But it may be that if these two are really close together and this one was higher, that these two wouldn't be significantly different and this one would. Let me just see what happens if I make my clay ones lower. So there's my graph there. Now they're all closer together here. And when I do my ANOVA, if I do my summary of this ANOVA, I can see that my p-value is still really low. That says that at least one of the means is different. But when I do my Tukey's Honestly Significant Difference, the difference between sand and clay has a really high p-value. And so that says that there is no evidence of a difference in height between sand and clay soils. But these two are both significant because this one is definitely higher than both of those. Yeah. So that is what they say. So you have to do those pairwise tests for Tukey's Honestly Significant Difference. My instinct is that if your lecturer wants to do this in their exam, then they will show you this table. and ask you to make an interpretation of the result. And the interpretation in this case would be clay and sand soils do not, on average, affect the height, not on average. The height of plants is not different on average between clay and sand soils, but for soil, just soils, the height is higher on average than both sand and clay, something like that. You have to mention all three comparisons somehow, possibly in 3 separate sentences, possibly combine it together. I will say that if your answer for are all the means the same is yes, because your ANOVA at the beginning gave you a high p-value, you don't have to do the multiple comparisons because you already concluded that they're all the same. So those pairwise tests aren't necessary if your ANOVA already retained the null hypothesis, because there's no point. It'll just give you the same information. Yeah. How are we feeling? And would you like to ask anything at this time? Sorry? Yep. So I think, well, I don't know, but all past Stat Prac I lecturers have done their exams this way. They have more likely given you a graph and they've given you like this table here and this table here and this graph and asked you to interpret the results. That's usually how they do it for ANOVA. Sometimes they ask you to maybe give you this table here and they won't put the degrees of freedom in and you'll just have to tell them what the degrees of freedom are, which you know is 1 less than the number of groups and number of groups less than the number of individuals. Yeah, but in general, and they may ask you maybe to tell them what the F value is because you know it's this one divided by this one. But other than that, they usually don't get you to do anything too detailed with ANOVA. That's what most lecturers in the past have done when students have come back to the Maths Learning Centre to tell me what's in their exam. That's how they've done it. And that's because they can't get you to type R code. That's not important to them because they know that because a professional statistician still looks it up every time anyway. I made some good guesses today, but I still had R to tell me if Tukey HSD was a real function or not, because it made a guess at what I was typing. So they know that you can't write code in an exam because that's not how coding works. With real coding, you try it and see if it works and then go, oh no, that doesn't work, I'll try a different one. So, but they might give you, yeah, so but they'll usually they'll give you the code, but just so that you know it's real, and then give you what the output that the computer produces. Like these tables, for example. That's how they'll normally do it. Yeah. And ask you to say, what's your conclusion? Yeah. They may give you a whole lot of QQ plots and say, are they normally distributed? That sort of thing. I've seen an exam question that goes, here's a whole lot of plots, like QQ plots and stuff. Assess the assumptions of ANOVA. And you'll have to know what the assumptions are. Yeah. And so you'll say, these plots tell me that that the individual groups are normally distributed, and this plot I have no way of telling whether they're independent without talking to the researchers. I have to do the individual standard deviations to know whether they're all similar or not. The rule is that the biggest one has to be not more than twice the smallest one, I believe. So, yeah. Okay, that's ANOVA. I have half an hour to go. And I just want to say, you can always come and talk to us at the Maths Learning Centre about it if you're a University of Adelaide student. If you're just a random person on YouTube watching this video who's not from my uni, sorry, you have to talk to your own people. But if you're from Uni of Adelaide, you can talk to us at the Maths Learning Centre about any of this. Particularly good at saying, hey, David, you said this in the revision seminar. What did you mean? That's a great question to ask me. Yeah, we're also good at interpreting lecture notes and assignment solutions and that sort of thing, making a good guess at how the lecturer did it. I'm the one who knows the most about statistics, just letting you know, but all the other staff will be able to look it up in your notes and make a good decision, even if I'm not there. But if I am there, wave me down and I'll come and talk to you. So, got half an hour. What do I talk about now? You can have your laptop back. While you're thinking, I'm going to number my pages. Yep. I can do that. Okay. We'll see how far I get, but I'll start with the proportion ones, hey? But I will say that there is an overall philosophy with hypothesis tests that is the same. They all share a few common features that it's important to know that those common features are there. So the first thing to know is that a hypothesis test is only capable of answering a yes or no question. Regression is designed to answer a what's the formula sort of question. How do I predict one thing from another? Confidence intervals answer the question of what's this number? So just while I'm at it, confidence interval answer a what's the number question. And regression what's the formula sort of question. So if your research question is like, how do I predict this outcome? Then it's a regression. If your research question is, you know, what's the mean salt in an avocado? That's a confidence interval question. But if your question is the amount of fat in ice cream produced from this factory really 2%? That's a yes or no question. And if your question is height related to soil type for plants? That's a yes or no question. So hypothesis tests answer yes or no questions, and they answer them via a p-value. So that's the first thing to know. It's a very useful thing. Maybe not so much for this course, but in the future, if you're reading a research article and you see a p-value, that p-value is attempting to answer a yes or no question. And so you can find the bit of the text nearby that says what the yes or no question is. It's just really useful, I find. Okay, and the second thing to know about a hypothesis test is that they all are designed by a similar process. And the process is you have to have a null hypothesis, you have to have a test statistic, and you have to know what the distribution of the test statistic is. So they all have a null hypothesis. And officially, they have an alternative hypothesis as well. They have a test statistic. Which will usually have a formula to tell you how to calculate it. And if not a formula, maybe at least some words. And that test statistic will have a distribution. Technically, it's the distribution if the null hypothesis is true. It has a different distribution if the null hypothesis is false, but that's not important. We're saying, what if the null hypothesis was true? What would happen then? And so we run down that road. So these three things are all part of a hypothesis test. And the reason you need them, you need this null hypothesis so that you can calculate this distribution. You need the test statistic so that you have something that has a distribution. And you need to know at the end of it, what the question you ask yourself is, the test statistic that I got from my data, how does it compare to this distribution of all of the test statistics that could have been if the null hypothesis was true? And that produces a p-value. So then compare the sample test stat to the distribution, and that gives you a p-value. And then you make the decision based on the p-value at the end. And it doesn't matter what kind of distribution you're using, as long as you have a kind of test statistic you use, as long as you have a distribution, you can get a p-value and then you can make your decision. That is how hypothesis tests work. They have those things. And the reason we have the calculations that we do is so that the distribution is one that we have a formula for, or at least a table for. Like you can make whatever test statistic you like, but if it isn't like a T and F, a binomial or something, if it's not programmed into R already, then you've got no hope of figuring out your probability. So you need to choose your test statistics so that it has a distribution that is in R that R can use. And so that is how they are designed. And they all have these pieces, and that's the important thing about them. But they also, because this calculus statistic has a formula or at least a description, they all go with, as well, before this, a type of data. That happens before this list. Each one of them goes with a kind of data. And that's really important, because if you don't have that kind of data, you can't do this hypothesis test. You would have to do a different one, or, yeah, you'd have to do it for a different one, or give up and collect new data. Okay, so our different tests are, we had a list before, and you said, let's start with the chi-squared and the proportions. Okay. Gonna have to help me with this bit, make sure I've got the formulas right, but I can at least tell you which ones go with which situations. So I'm going to start with the chi-squared test, which is like the last one that you learned, I think. Is that right at the end? Yeah. So just so you know, the chi-squared test. And this chi here is the Greek letter, that Greek letter. And the capital for that looks like an X, by the way. And I believe it is the letter at the beginning of Christ in Greek. So it makes a k sound, not a ch sound. So do not call it the chi-squared test. Everyone will look at you funny. or go, oh, look at this uneducated person who doesn't know how to pronounce this letter. If it was Greek, you could call it the chi-squared test. But in English, we tend to call it the chi-squared test. So we pronounce it as chi. Okay, chi-squared test. And the chi-squared test answers this kind of question. It's saying, does being in some sort of category make a difference to which outcome category you're in? And officially, it can't actually tell which way around it is. So it's saying, is being in one category related to how likely it is to be in another category? And the short version of this is, are these two categories associated? Which is the short version. But this is how I think about it. Because most chi-squared tests, there is one that is an outcome and there's one that happened before. So it's like, do people who a second, there's a word for it. Like, do people of different genders, are they more or likely to participate in volunteer work? Do people, does having chili in your meal make a difference, seem to make a difference to whether you feel hot after eating it or not? And anything that you could think of. Does treating rabbits with love and care make a difference to whether their wound heals faster? So like, does the wound heal within 1 day or within 1 week or longer? Like, as long as you can treat them as categories, it doesn't really matter what you do. You can always use the chi-squared test. And the way and so are these categorical variables associated? Or it could be, is being in one of these categories, does it make a difference to which of these categories you end up in? And the null hypothesis is no. They are not related. Variables are not associated. And the reason that's the null hypothesis is the null hypothesis is always the thing that has only one way to be. There is only one way to not be associated, and that's just everything's random. But there are many, many ways to be associated. And so since that's the one with only one way, that's the one that's a null hypothesis. Yeah. And it is, in fact, usually done with the words, the null hypothesis. You could pitch it in terms of probabilities, I guess, if you wanted, but whatever, it's fine. And the chi-square test is called the chi-square test because the distribution that it uses when we get to this point is a chi-square distribution. So we've already got our type of data, which is this, 2 sets of categories, and the data will normally look like this. You'll have your subject, 1, 2, 3, 4, 5, etc. And it'll be like, what did I have? Just a second. Type of chili and feel hot. And so we could have no chili and no, no, yes. And we could have, whoops, there's a 4 there. We could have powder, yes, yes, no. And we could have flakes, yes, 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 something like that. It'd look like that. So this is what the data would look like. Every individual would have a an answer for one of the categories and an answer for the other category. And R would be able to make a neat little table for you. And sometimes the data doesn't start this way. Sometimes the data is already neatly summarized for you in this way. And you have type of chili, no, powder, flakes, and hot, yes or no. And you have a neat little table like that. And it's set up with how many people who had no were hot, how many people with no were not feeling hot. And all these numbers are in this spot. This is a two-way table, they call it. Possibly a contingency table. Not sure, but that's what it's sometimes called as well. They will not have called it this name in this course, but I have heard it in some courses called a confusion matrix. So, for example, you might have like 5 people said yes and 10 people said no. And with the powder, it's more like 8 and 7, and this one's more like 11 and 4 or something like that. And they don't have to add up all to the same thing, but these ones do today. Maybe I'll make one of them different. Let's make this an 8 as well. And so this is 15, 16, 15. They're the totals. And so they'll often be totals. So this will be 46. What's this? 19 and 5 would be 24. And that would be 22, like that. Okay. So this is the contingency or two-way table. Sometimes you're given it like that and you have to find the totals yourself. Sometimes the totals are put in already. And the question is, well, are they related? It seems to me that if you have chili in your meal, you tend to feel hotter than if you don't. I'm making this up. I don't know if that's true. It feels like it should be true, but you never know. It depends on your background, I suppose. If you're used to eating chili, you might feel different. Yeah. When you actually do the calculation, you have to. So that's the data. I'm up to this point here. I've got what the data looks like. I've got a null hypothesis. The next thing is a test statistic. The test statistic is a chi-squared. And it's equal to, and it doesn't have a formula. It has a description of how to do it. The formula might have been a sum sign and observed minus expected spared over expected. Does that sound familiar? I mean, that's how I do it. Pretty sure that's it. So this means sum here. It's the Greek letter sigma, which makes an S sound, S for sum. That's the capital sigma. The small sigma is the one we use for the standard deviation. And what this means is that observed is exactly this table as it is. That's from the table there. So this observed is this bit here, what that is. And the expected is, all right, well, if eating chili or not, or the type of chili you have, doesn't make a difference to whether you feel hot or not, then, it's approximately 50-50 here, like 24 and 22. That percentage should be the same in all of these groups. Because if chili doesn't make a difference, the percentage of yes, no should always be the same. And so what I'm going to do is I'm going to figure out, what percentage this is of 15, and that's what I would have expected to be here. What percentage of this is this out of 15, and that's what should have been here. What percentage of this percentage here out of 16, that's what goes in that spot. And so that's how you calculate it. And so you say, for example, for no and yes, no chili, and yes for hot, then all the yeses together is 24 out of 46. That fraction. And that fraction of the 15 is what I expect to be in this spot. So the expected value for no and chili, no for chili and yes for hot is this. And the expected value, let me just pick another random one for flakes, chili, and no for hot. Well, it's 22 out of 46 for the no's, and there's 15 in that group. And so that's what I did. Yeah. And that's how you do it. You do this out of this times this, or you can do this out of this times this. It doesn't really matter. It works the same way either way. And you figure out all of those answers and you make a table of those. No, powder, flakes, yes, no. So this number here goes in that spot there, whatever this is. And that is what calculators are for, people. What have we got? 24 out of 46 times 15, 7.8. And so that goes in this spot. And this one is whatever it is. I know what that's going to be. That's going to be 7.2. And that goes in this spot. And then you'd fill them all out. And then what you do is you'd go this minus this squared divided by this and figure that out. And this minus this squared divided by this and figure that out. And this minus this squared divided by this and figure that out and do it for all 6 of them and add them up. Yeah, so this is the observed. And this is the expected. Yeah, but officially to get the chi-squared test, you have to do the entire table in order to do it. So most exams, they just get you to figure out one of them, just to prove that you know how to do it. Yeah. And then you have to add up all of those things. So officially you could do an observed minus expected squared over expected table and get all these 6 numbers and you add them all up. So yay. And that's what the chi-squared statistic is. Now, you know how I said Fisher was very clever? Pearson, who invented this, very clever. Like, what the hell? Like, honestly, that's amazing that this calculation is something that anyone even think of, and then even know what the distribution is. It's the chi-squared distribution, which is programmed into R. Obviously R wasn't invented when the chi-squared test was invented. They had to do a great number of calculations and put all the numbers in a book that you could look up 100 years ago. But now we have computers to do it. And so you get your chi-squared was going to be like your 5 minus 7.8 squared over 7.8 plus blah, 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 blah. There's 6 of them, right? So yeah, 5 minus 7.8 divided by 7.8. And sorry, it was a 9. And then the last one, this one down here is it's a 4, damn it. 4 here minus 7.2 squared divided by 7.2. And you'll get an answer, whatever that answer is. And that answer you will look up in the chi-squared distribution. Chi-squared with some number of degrees of freedom in this spot just here. I don't know how they write it in this course. They probably put a little number at the bottom, I don't know. With degrees of freedom. When you do a t-test, the degrees of freedom is 1 less than the sample size. When you do regression, the degrees of freedom is 2 less than the sample size. When you do ANOVA, you've got 2 different numbers for the degrees of freedom, 1 for the groups and 1 for everything else. And when you do chi-squared, it has nothing to do with what your sample size is. It's not related to the sample size at all. It is related to the sample size of this table. Are you ready? This is my favorite way of doing it. Here's my table with my 6 boxes. I'm going to ignore the totals. You cross out 1 row, 1 column, and 1 row. The degrees of freedom is the number of boxes that is left. 2. Yep. So the chi-square test can have any size table. And you just cross out 1 row, 1 column, and whatever number of boxes is left, that is the degrees of freedom. In your book, it probably says rows -1 times columns -1. Well, that's how you figure out how many boxes are here, but it's usually easier to just draw the picture. Yeah, it doesn't matter which one, but I usually do the last one. Because otherwise I have to bridge a gap that you've... It's literally how many boxes there are, not what's in them. And so as an example, if I had something with, 5 categories here, and I wanted to know how it was related to something with 3 categories here, then I would have my little table and I would cross out 1 row and 1 column, and I have 8. So I would have a chi-squared with 8 degrees of freedom. And the reason it is that the idea is that you're imagining all of the other tables that could have happened, but keeping the totals the same. So you're saying that what if you collected other data and it still had the same totals, but this bit was different? Then you wouldn't be, if you change this number and this number, then you would have to fill in all of these to keep the totals the same. And so that's how many boxes you're free to change without changing the totals. That's why it's the degrees of freedom. So don't know if that helps you, but I like the drawing. The R-1, C-1, and I'm a mathematician and it still confuses me, but this I can do. Yeah. Yeah. And look, the thing is that your chi-square distribution, the higher the degrees of freedom, like the chi-square distribution looks like this. Crap. Where'd my eraser go? I had one. Yeah. The chi-square distribution looks a lot like your F distribution. It's actually skewed. But the higher the degrees of freedom, the further out this hump is, and the harder it's going to get low p-values. Yep. It doesn't matter because it doesn't matter. It just matters the shape of the table, not what numbers are in it. See how this is a 2 by 3 table? And I cross out 1 row and 1 column. That leaves me with 2 boxes. This is also a 2 by 3 table, and I cross out 1 row and 1 column, and I get 2 boxes. No, it's not based on how many individuals are in those boxes. It's just based on how many boxes there are. Important question. Thank you. Yeah. So without even doing any of the calculations, you can know what the degrees of freedom is going to be. Yeah. And that's just so that you can tell the computer exactly which chi-square distribution to use to get the p-value. And then after that, it's the same. P-value is under 0.05. Yay. I'll conclude that there is an association. P-value is over 0.05. No, not as an association. And that's the deal. Oh, it's 4 o'clock already. My goodness. Well, I'm glad it wasn't different tests. It was just one test, but I did talk about the general vibe of tests at the beginning, I guess. So officially, the chi-square test can be used for any situation, even when there's 2 and 2. And when there's 2 and 2, you get 1 degree of freedom. But in the 2 and 2 situation, you can also do the Z test for a proportion, because you can say, all right, well, I can actually, I know I'm going over, but here I am. Crap, it's the 2 proportion test. The 2 proportion test is also designed for this situation. Category A and B, category yes and no, but it is only designed specially for when this outcome is yes or no. And in particular, you're only focusing on the yes, and you're not worried about the no, because obviously everyone who isn't yes is no. So in the 2 proportion situation, it's still a story like this. You've got like, oh, are people in the city or people in the country, do they would they favor this person as prime minister? But then the other option is they wouldn't, right? And so about each person, you can write down, you've got each person, 1, 2, 3, 4, and you can write down, their category number 1. And these are all A's, and they have a yes, and maybe some no's, and these are all B's, and maybe more of them are yeses. And that's what the data will look like, and it looks like a chi-squared kind of data. But if you only focus your attention on the yeses, and the other people are still there, then you can think about it in a different way. If someone asked me, okay, in the country and the city, are people more likely to favor this person as the prime minister or not? You would say, well, 20% of the people in the country favor the prime minister, and 40% of them in the city do favor them as the prime minister. And I'd tell them those 2 percentages. That's what I would do. I wouldn't probably tell them the no's, because that's obvious. If it's 20% yes, then it's 80% no. But because the way I tell this story is as percentages, I can pitch my story as being about proportions. I can say that proportion A is the proportion of yes in category A, and PB is the proportion of yes in category B. And then my null hypothesis can be, well, that those 2 proportions are the same. And that is a way of pitching the same question that you could have pitched as saying that location is not related to favoring this person as prime minister. That would be the way of saying it in a chi-squared situation, but in a proportion situation, this is the way of saying it, that the 2 proportions are equal. They answer the same question. They actually get the same p-value. It's quite remarkable. But when you read the question, if they tell you percentages, then they're thinking about this. Yeah, that's H0, and HA is that they are not the same. So we know what the data looks like. We know what the hypothesis is. This hypothesis specifically mentions some parameters, and so we have to tell the person what the parameters stand for, and the parameters are called P. And then I believe in your notes it will probably say P1 and P2, but I much prefer to label them by what the actual categories are called. If it was country and city, then maybe I would have done R and C for rural and city, maybe. Or R and M for rural and metro, something that I can remember. And then you have to do a calculation based on what actually happened in your data. And that calculation produces a Z statistic. And it's called Z because it's from a standard normal distribution. Z stands for Zahlen in German, which is number. All the test statistics were called Z 100 years ago, and they had to relabel them later. Yep. A one proportion test isn't about relationships. I'm good. Can I just finish this for a second and come back to that? And so the Z is going to be PA hat minus PB hat over, oh God. Pretty sure it's that. Could be wrong. Just check that. Where the P hat there is the proportion that would have been if you lumped them all together into one giant group. And the N1 is how big group 1 is, and the N2 is how big group 2 is. Is that right? Oh, okay. Oh, yeah, you're right. You're right. Like that? Okay, cool. I'm glad. Thank you for checking it. This P hat is the combined percentage. So this P hat is made by saying the proportion of yes in the combined group. So if you had like, 30 people out of 150 in group A and 10 people out of 200 in B, then your PA hat is 30 out of 150. Your PB hat is 10 out of 200. And your P hat is, well, if it doesn't matter which category you're in, then it's just one big group. And so that's 40 people out of 350. So just combine them together into the entire big group. That's how that works. And like this N1 that they're talking about is the 150. And the N2 is the... And then the distribution is the normal distribution with mean 0 and standard deviation 1. That's how they write normal distributions in this course, right? The standard normal. Okay. Now you did ask, so I have one page left. What about the one proportion test? In a one proportion test, you don't have two variables, you've only got one. And it's just, and the category is like yes and no. And that's the information you have about each individual person. So the data looks like 1, 2, 3, 4, 5, etc. And there's just a whole lot of yeses and a whole lot of nos. Officially, that's what the data would look like. And mostly it doesn't even look like that. It just looks like yes, and there's like 20 of them, and no's, there's like 85 of them or something. It just says how many there are. That's what the data looks like. And the question is always, is the proportion of yes equal to this number I first thought of? So is sometimes it's a proportion with no, it doesn't really matter. Is the proportion with yes equal to, and there's a specific number. So like, is it 50%? Is it 0. Sometimes they do it as a percentage, sometimes they'll do it as a decimal. Like, is the proportion 0.2? Because you could ask, like, do a majority of people, of school kids, finish all their homework? And that question is the proportion 50%? And then the null hypothesis is that the proportion equals to whatever the number is. And the alternative is that the proportion is not that number. And then the test statistic is a Z as well. And it is P hat minus the P from the null hypothesis is P1 minus P0 on N, probably. Yeah. You can see I've been doing this for 16 years. That's how long, no, it's not how long it takes to remember it, but that's why you get a formula sheet, so you don't have to remember it. Yeah, and so most lecturers give you a table at the end of the course that summarizes all of this information. Did your lecturer give you one? Okay, good. And that is a useful thing to put on your formula sheet with a few annotations to give you some extra remembering of how it goes. Because that table doesn't give you this information. So, well, I really am going to stop now. It's time to go home. So I'm going to stop the recording. Thanks for watching.